Welcome to the SFT Creationist versus Evolution podcast. This is episode 1, and we are debating genetic entropy. I have Praise I Am, who will be moderating, keeping time, and taking questions for this first epic episode on the SFT debate podcast. Praise I Am, I'm going to hand it over to you for some words of introduction.
As Praise I Am, I'll be sitting as the mod tonight. I'll just be here guiding the discussion along, but before the discussion gets started, we'll just do brief intros so the audience can get acquainted with the speakers tonight. So we'll hand it off to Donny first, since he is the main man of the channel. And what's up, Donny? What's up, dude? And just a few things about what you're up to, and get this for the audience so they maybe get a little bit more informed of what's going on tonight, and then we'll hand it out to Taylor after that.
Awesome. Thank you. Praise I Am. Since this is episode 1, I see some questions already coming in. And so, yes, this is the new SFT podcast. So these debates are going to be audio only. And so we decided to do them live on YouTube for people to enjoy. Then we, myself, I'll go in, edit it a little bit, and then we upload them to our SFT podcast website. And so all you're going to see during the debate itself is the SFT podcast creation versus evolution conversations template. And so Praise, good to have you here to moderate. Snake was right. Taylor from the Snake was Right YouTube channel. Always a pleasure. I know he's had a ton of debates. We've gone back and forth with each other numerous times over the last 3 or 4 years. I've done 100 formal debates. If we were to include informal debates, impromptu, open mic discussions, it's probably closer to 200. But I am really looking forward to these series of podcast debates. And so I've already got a few lined up. Again, this is episode 1. We're specifically debating, is genetic entropy a legitimate problem for evolution? Of course, I would say yes. So I'm in the affirmative. And Taylor would say no. And so Praise, thank you so much for being here again. And yeah, that's basically it for my intro.
Man, looking forward to this. This is sort of a new thing that is being introduced here, so I can't wait to see how it works out. But Taylor, also, maybe you could give a brief intro for the audience just to let people know about yourself, what you're up to, and all that stuff.
Hey, well, you know, same as always. I do religious, scientific topics, and sometimes politics and philosophy, and I'm, you know, I try to distinguish myself from my fellow atheists because I am anti-moral relativism, anti-communism, but I try and do source methods for all topics. And I also run a debate channel called Debate Cafe with my best friend, who's a actual professional debate coach. So we're going to be starting back of regular debates, and check us out.
Awesome. Fantastic. Yeah, check that out. And before we get started here, I just want to briefly give the format for the audience. We'll have 12-minute openings, 8-minute rebuttals, a 50-minute discussion, and then a 5-minute closing. And then we'll have the Q&As with super chats if there's time left. I'm not sure. We'll see how it plays out, and we'll just play it by ear. But SFT will start us off tonight. And whenever you're ready, Donny, I'll start the time for you, and I'll give you a 2-minute warning as well.
Well, thank you very much there. Praise I Am. I made a joke that these podcast discussions or debates are a little bit more relaxing than your formal ones. I didn't even have to put on my blue SFT shirt today. And Doki Doki Bible Club, my brother in the chat, says, we know you're wearing one anyways. I've got 7 blue SFT shirts, 1 for every single day of the week. Okay, so with a little humor out of the way, let's let's get right into it. And actually, one thing I should notice, since I'm actually in the discussion itself, for those that want to ask audience questions, please make sure you're tagging at Praise I Am. Would you say Praise for questions?
Yes, yes.
Okay.
Praise I Am. I'll just tag it right now.
Awesome. Okay, I'm going to start my timer here. All right. What is genetic entropy? Genetic entropy is a concept built on the observation that the mutation rate is high and that most mutations are too subtle to be removed by natural selection or differential reproduction. There exists variation in reproduction numbers within a population, as in some members of a population will reproduce more than others. This is why a mutation must be large enough to affect reproduction in order for selection to see it and therefore remove it from the equation. Selection is basically a fine-tuning mechanism, and it keeps a species as strong as it can be. Selection also involves the death of individuals. This means selection is limited. You can't select away an entire population, since that would result in immediate extinction. It can only ever slow down the degeneration process. It can never solve the degeneration problem, as we will see in this debate. Now, genetic degeneration and the accumulation of low-impact mutations is a very serious problem for evolutionary theory. It is a challenge that has not yet been answered. The answer to tonight's question, therefore, is yes. Genetic entropy is a legitimate challenge. It's a very real challenge to evolutionary theory. Genetic degeneration has to do with what? Well, it has to do with mutations. Mutations are mistakes or errors that occur during the DNA replication process. They are essentially changes in the nucleotide sequence of DNA. Mutations can also be caused by environment, from chemicals or radiation, for example. Even though we have these amazingly designed, these intricate DNA repair systems that are built into the genomes of life, evidence of forward thinking that brings us right back to the forward thinker. Well, this replication process, even in light of these incredibly designed DNA repair systems and enzymes, the replication process, it's imperfect. And many mutations get through each generation. Now, according to evolutionary theory, the evolutionary story, mutations are the driving force for evolutionary change. To take your fish to amphibian, your amphibian to a reptile, and your reptiles to mammals, this requires the necessary variation or genetic diversity for selection to act upon. And according to evolutionary theory, mutations are what provide this necessary variation for selection to act upon to take single-celled like ancestors into whales over billions of years. Genetic degeneration or genetic entropy relates the greatest to the long-term persistence of complex organisms, such as higher mammals, humans and elephants, for example. Complex life forms such as humans have relatively small population sizes. They also have slow reproductive rates. These organisms will have the most challenging time surviving the consequences of genetic degeneration, since deleterious mutations affect higher or more complex organisms the most. Now, every time the cell divides, more mistakes are added to the genome. Again, mutations are basically just changes in the nucleotide sequence of DNA. Most of the mutations we accumulate, though, in a lifetime occur in somatic cells. An example of a somatic cell would be a skin cell. And so, fortunately, those are not passed on. but they are a primary reason why biological organisms age and eventually die. Now, although mutations in somatic cells are not passed on to the next generation, mutations that occur in reproductive cells, egg or sperm cells, for example, can be passed on to the individual's progeny. The mutation rate in humans, it's high. It's roughly 100 new mutations per person per generation. Michael Lynch documents the human mutation rate in his paper titled Mutation and Human Exceptionalism, Our Future Genetic Load. Anybody familiar with my debates knows that I love slides, I love visuals, and I love backing up all of my arguments with citations. And so you can either see my previous debates, my previous presentations on genetic entropy, and also my articles and books for visuals and the citations for you to look into. And so he says an average newborn contains roughly 100 de novo mutations. Okay, so moving on here. To prevent genetic decline and eventual extinction, there has to be a type of selection that can filter out these harmful mutations accumulating each generation. Population geneticists struggle to explain how species, not just in humans though, how they can survive for long periods of time in light of this high mutation rate. Natural selection is also severely hindered by something termed selection interference. This is because selecting for one trait interferes with selecting for another trait. There's just far too much genetic noise that results in severe limitations in selection. Selection interference profoundly limits selection efficiency. Now, the reason for this is when you have billions of traits segregating in the population, the selection process actually starts to work against itself. This means selection can only end up choosing from the best and the worst mutations. But the nearly neutral mutations, your low impact mutations, they build up and they continue on unchecked and unnoticed by selection. That means they're only subject to genetic drift. And so they spread, they cause disease, and they degenerate. And there's nothing selection can do about it. The major problem for those that want to believe whales and strawberries are related through common ancestry is that mutations are catastrophic. Remember, it is the evolutionist that explains the vast majority, if not all, DNA diversity and variation as being the result of what? Mutations over time. Us as biblical creationists, we have a very different explanation for the origin of the majority of your autosomal DNA differences, your nuclear DNA. And that would be through what is called created heterozygosity or design diversity. But it's a problem for the evolutionary model because they are explaining almost all genetic variation as being the result of disease causing mutations. Mutations, they degenerate. Simply put, they are destruction and not construction. Mutations are the main source for death and pain. What can we do to stop genetic degeneration? Serious population geneticists acknowledge this real problem of deleterious mutation accumulation. Here are some important quotes. This is one from Kitely, Peter D., and Michael Lynch. And they say, in summary, the vast majority of mutations are deleterious. These are not young earth creationists. These are evolutionary population geneticists that are saying, and I quote, this is one of the most well-established principles of evolutionary genetics, supported by both molecular and quantitative genetic data. That is a quote from a paper titled Toward a Realistic Model of Mutations Affecting Fitness. Dr. Kimura, world-famous population geneticist, said under the present model, effectively neutral, but in fact, so here's the answer to the question, what does effectively neutral mean? Well, Kimura says, but in fact, very slightly deleterious mutants. accumulate continuously in every species. And then Dr. Komuro goes into the rate of loss of fitness per generation, and it is high. It is very high. And in the paper titled The Distribution of Fitness Effects of New Mutations, Iyer, Walker, and Kitely say, it seems unlikely that any mutation is truly neutral in the sense that it has no effect on fitness. Notice this next line. All mutations must have some effect, even if that effect is vanishingly small. That's from the paper again, The Distribution of Fitness Effects of New Mutations. And so
2 minutes.
Thank you very much. And so we have these nearly neutral or effectively neutral mutations that are only slightly deleterious to the information systems of biological organisms. They're invisible to selection, but they're not strictly neutral. And so they accumulate like rust molecules on the car. And over time, the genomes of living organisms, they what? They rust out. They degenerate. Christopher Roop and Dr. John Sanford sum up the problem of genetic degeneration perfectly. And so I am just going to quote them from Contested Bones. The human mutation rate is roughly 100 new mutations per person per generation, they say. The ape mutation rate is similar. Almost none of these mutations are beneficial. The new ENCODE findings reveal that most of the human genome is functional. Hence, most random changes in the genome must be deleterious. Notice this part. Even if 90% of the genome is perfectly neutral junk DNA, which is no longer feasible, there would still be about 10 harmful mutations arising in every person, every generation. Even the most fit individuals are still more mutant than their parents. So even intense selection against the less fit cannot stop mutation accumulation. We've got just over 30 seconds here. I'll start to wrap up and finish this quote. Christopher Roop and Dr. Sanford say, because most deleterious mutations cannot be selected away, they will accumulate continuously from one generation to the next. And here's the last part of my opening statement. Give me 20 seconds here. The reason we as humans are not extinct is because we are not the product of evolutionary processes. We are a product of special creation. Since man was created thousands of years ago, it makes sense that we have not had the necessary time to go extinct through deleterious mutation accumulation. If humans have been evolving and adding mutations to the gene pool every generation for millions of years, evolving through primate ancestors, we should not be here. We would have gone extinct a very long time ago. Thank you very much.
All right. Thank you so much, SFT. Now it is Taylor's turn. If whenever you want me to start the timer, Taylor, I'll start it for you, and we'll get into your intro.
All right. So first of all, I think that the word entropy is chosen for a reason. It's the concept it's supposed to be, it's inevitable. So that's a requirement for this concept of genetic entropy. But it kind of betrays this misunderstanding of what entropy even is. And I think that would be a good thing to discuss to kind of wade into the topic. So entropy actually does not mean continuous degradation. We observe systems becoming spontaneously more complex without any intelligent input all the time. One example is the abiogenesis experiments. Even though, I'm not using them to argue for the origin of life at this point, it does show unambiguously that chemicals will spontaneously form complex formations through various reactions. And so it's the way different processes interact that gives us complexity. If one process is limiting in a specific way to another, that means only products that make it past that limitation will be left. So you're left with a biased pool of products. So like natural meteorites are found with the biases for certain amino acid enantiomers due to these natural processes, when random math would tell us that it should be roughly 50-50. That's not what we see. Chemistry can act against entropy. Which if you actually took like collegiate level chemistry or something, You actually have to calculate entropy, things like that. Spontaneous order can form in chemistry. And so the claim that it's inevitable degeneration of all things, like as a law of physics, is just a false interpretation, because temporary order forms spontaneously by increasing entropy over here and decreasing it over there. And that's observable and demonstrable in non-evolutionary sciences. So it's not just all going in one direction all at the same time. Some parts of the universe increase in entropy while others decrease, and likewise complexity. So the main claim of genetic entropy is that it's inevitable. And so this is based on just a handful of pretty obvious mistakes if you look at how they came to these conclusions. So John Sanford, the inventor of the term genetic entropy, writes in his book, Genetic Entropy, quote, "It can be very reasonably argued that random mutations are never good." Nothing actually backs this claim. He misuses Moto Kimura's data, and this fundamental mistake is what his entire book is based on. Sanford says Kimura obviously considered beneficial mutations so rare as to be outside of consideration. Now, Kimura, in one of his papers, did say he disregarded beneficial mutations, but Sanford's either ignorant or dishonest about why. Adding beneficial mutants in his paper completely overwhelmed selection among neutral mutants, and evolution rates skyrocketed in the positive direction. So Sanford's entire concept of genetic entropy is based on this number taken from Kimura, where he deliberately leaves out beneficial mutations, which he acknowledges isn't realistic. And if included, it very effectively counteracted slightly deleterious mutation accumulation. And Kimura said this. And he didn't leave them out because they're so rare. He did it because he wanted to study neutral selection only. So this foundation of Sanford's idea is actually just cherry-picked from an unrealistic, very specific niche type of calculation. So I guess Sanford ignored this, or doesn't know about it. He will often set beneficial mutations to 0 and set his population size to 1,000 in his supposedly realistic models of evolution, despite it being explicitly unrealistic. Population sizes at about 1,000 and under are highly vulnerable to extinction via mutational meltdown, which is kind of what genetic entropy is. On timescales, approximately 100 generations, according to Lynch et al., 1995, where they study extinction via mutation accumulation. And this only occurs in nature in these very specific circumstances. And it just so happens that Sanford's conclusions about the human race are based on very narrow conditions in these dangerously low population levels of 1,000 with no beneficial mutations, which is extremely unrealistic and at risk by design. And it's interesting then that Sanford stands by the biblical tale where the entire world was populated by a single incestuous family twice. And so even by his numbers, we'd be dead 100 times over. And it's obviously false that there are no beneficial mutations. So let's talk about that for a minute. For example, in humans, there's a mutation that confers human resistance to HIV. It's a deletion. So there's this concept called fitness landscape. So fitness goes up and it goes down with peaks and valleys. And often what happens is something is added via mutation that's harmful, and then that mutation itself further mutates, or there are other mutations that affect it, and it's pruned away, and then it's better than it was before the addition. And that's exactly what we see in nature and in the laboratory. One of the drivers of adaptive peaks is compensatory mutations, which are effectively mutations of deleterious mutations. The mutations themselves later mutate. That's one of the things that Sanford's models doesn't account for. And these compensatory mutations fix them. So fitness goes up and down. Sanford's model doesn't account for this. Mutations have fixed effects in his model, and he generally adds in 0 beneficial mutations or compensatory mutations. They've been shown to suppress deleterious and pleiotropic interactions between mutations and to fix individual mutations. So this is exactly the problem that genetic entropy brings up as a challenge. So there's different mixtures of neutral or slightly deleterious mutations that can actually flip and become beneficial if they interact well with each other. And this has been studied in animals, which can help stabilize protein mutations, like in hemoglobin or egg proteins. So what's deleterious in one mixture is compensatory in another, or some compensatory mutations are specific to certain effects or even specific deleterious mutations. In salmonella experiments, they're mutated and evolved into a less fit strain after evolving antibiotic resistance. They went into a valley, and this trait negatively affected protein synthesis, bacterial growth, and virulence. But then they kept evolving them and put them back into wild conditions where they fully recovered all of those measures of fitness, and they retained their antibiotic resistance, which showed in real time that not only did the negative mutation accumulation get corrected, but they were actually more fit than before any of this mutation occurred. But they had to go down and then back up. So it's not a straight line. And compensatory mutations are more likely to affect the more severe deleterious mutations. It's about a ratio of 9-to-1 that can fix them. So Sanford's ignorance on this topic in his models displays a severe problem for the genetic entropy's inevitability and just its working concept. There were experiments breaking hemoglobin. It was shown that random compensatory mutations could effectively fix its functions, and it wasn't back mutation which restored the old sequence. It was a new sequence with the same function. Compensatory mutations are so powerful that they've studied these fish that don't go through recombination, and they ran models, and just compensatory mutations could basically halt genomic decay in these species. It's important to constantly remind ourselves too that deleterious mutations are not deleterious in every individual. It's based on what mutations they have and the environment. And Sanford claimed to test this, but again, he set beneficial mutations to 0 and population size to the dangerous range of 1,000. Even though we saw compensatory mutations are important and frequent, and that's why he doesn't add them. They give effects that shouldn't be possible if genetic entropy was true. Epistasis will help bring down the deleterious mutants as well, because people have different combinations of different mutations, and basically that means that there's different levels of selectability. And Kondrashov says that epistasis can effectively halt the action of Muller's ratchet, which is essentially genetic entropy, but only in certain conditions. And of course, no single method will ever be able to solve deleterious mutation accumulation on its own, but these processes do it simultaneously, and Sanford tests these independently, but never together, even though in reality, we see them acting in organisms together, not separately. So we've demonstrated that Sanford's model isn't realistic because it leaves out compensatory mutations and other beneficial mutations, operates in highly dangerous zones of genetic diversity, possibly intentionally, and tests these variables independently, even though they operate together in reality. Sanford's model, Mendel's accountant, has only been published in computer science, not in the biological sciences, and this is why. So just to go over how absurd the concept on paper is, Sanford claims nearly neutral mutations are invisible to selection and yet simultaneously harmful to the population. This is a contradiction. Evolutionary fitness is defined by being selected for or against, but then Sanford claims fitness goes down while mutations are invisible. So unless he's claiming the entire population just suddenly hits a wall and can't take anymore, this is a fundamental contradiction. Once accumulation starts to be harmful, either epistatically or otherwise, that crosses the threshold and is now visible to selection and is maintained at the mutation selection balance. In other words, if there are high numbers of deleterious mutations, the number of possible new deleterious mutations decreases and the number of possible beneficial mutations increases, and there's about a 9-to-1 ratio of compensatory mutations that can fix any individual deleterious mutation. We also saw that there are well, you heard that there are several mutational increases to fitness and purges of deleterious effects in real time in living organisms, not computer models, that shouldn't be possible if genetic entropy was true. And there are several species like mice, bacteria, and viruses that should have gone extinct by now due to their fast generation time if genetic entropy was true. So these facts are preclusionary to genetic entropy. It's based on unrealistic numbers, unrealistic models. Sanford and Carter produced pretty bad methodology. They produced a paper about flu extinction due to mutation accumulation, and it claims a strain of H1N1 went extinct in 2009. Meanwhile, in the paper, there's data for it surviving till 2012, and they're comparing a 1918 avian flu to the human H3N2 seasonal flu and claiming they're the same strain. So this is just bad methodology on every level. Every piece of data backing genetic entropy is literally just clownery and cherry picking.
All right. Thank you so much, Taylor. We're going to move into the next portion of this discussion tonight, and that is the 8-minute rebuttal session. So whenever you're ready, SFT, we'll start your timer. Also, do you want me to give you a 2-minute warning with this as well?
Yes, please. Yes.
Got it.
And those are the nice things you have to say about it, eh, Snake?
Mm-hmm.
Okay, so here we go. Just 1 second. Start my timer. And we're moving quick. So I'm starting my timer now. 8-minute rebuttal. Here we go. So Taylor talked about the word entropy and abiogenesis. Entropy, when applied to genetics, simply means that genomes are going downhill and not uphill. There is a general trend towards degeneration, and that general trend towards degeneration has to do with these low impact mutations that are accumulating from generation to generation. So I always say to the evolutionists that have this problem with the word entropy in light of what we're discussing here, you can simply use the term genetic degeneration instead. In terms of abiogenesis, I don't even need to go into abiogenesis to refute a naturalistic origin of life, since if mutation accumulation is indeed an unsolvable problem for evolutionary theory, and therefore humans are not related to chimpanzees and strawberries because of it, then by definition, abiogenesis did not happen. So I can stay as close to home as possible. Let's stay within, human evolution, if you'd like. Because genetic degeneration, the reality of genetic degeneration, tells us that humans and chimpanzees are not related. And so if humans and chimpanzees aren't related, then humans and strawberries definitely aren't related. So Taylor mentioned Kimura, and he said that Sanford ignored or misrepresented Kimura. Actually, I hear some background noise if you want to mute. That is not the case, though. Kimura simply claimed adaptive mutations. And you can see the quote yourself. He just kind of threw it out there. He claimed that this problem, which he acknowledged was a problem, nearly neutral mutation accumulation, is real. But he simply just claimed without evidence that adaptive mutations could solve the problem of low impact mutation accumulation. That's all he did. He just made an assertion. He made a claim and then moved on. But we have more data today that falsifies that claim. Beneficial mutations, they're rare. They occur about 1 in a million. And when they do occur, for the most part, they're reductive. Think of sickle cell anemia, for example. Yes, it has a localized benefit to those with malaria. These deformed hemoglobin proteins, okay, people with sickle cell anemia, they can thrive in cases of malaria, but sickle cell anemia is due to a broken gene, broken cell, broken protein. And so it's reductive. It's still functionally compromising to the organism. Now, Snake mentioned one or two, an HIV example of a beneficial mutation that he thinks is truly beneficial and not reductive or functionally compromising in any way. But that's focusing on the minutia. What we need to do is focus on the bigger picture. The bigger question, the major problem is what? Net gain versus net loss. And so for sake of argument, you can have 50 truly beneficial mutations that are not reductive. I don't believe they exist. I believe any beneficial mutation manifested by the evolutionists, we could demonstrate is either the result of epigenetic change, and therefore the result of the built-in capacity to adapt in the first place, or reductive, loss of a pre-existing system, pre-existing systems breaking down. Basically, we see that in bacteria. There's many papers about bacteria and how they experience reductive evolution. We see that in the Lenski experiment, where Lenski's bacterial populations, due to several episodes of adaptation, they've actually shrunk in functional genome size. They've painted themselves into a corner. They're lazy. If you put them back into the natural environment, they would be dead on arrival. And so all of their mutations are reductive in a sense. They're losing genes short term, but it's actually long-term degeneration. And so Dr. Sanford, he didn't ignore Kimura's statements. He recognized the fact that beneficial mutations are far too rare to ever counterbalance the damage. Now, Taylor also talked about compensatory mutations basically that will compensate for the loss being done by these degenerative mutations. Okay, but these kind of mutations, they won't counterbalance the damage. Back mutations don't help either because they're far too rare. It's as if they are not occurring. They're occurring, but the genomes of living organisms are being flooded with so many deleterious mutations, and the mutation rate is so high that it's almost like they're not occurring. Okay, so trying to compensate for degeneration through these types of compensating mutations is like trying to fix your vehicle that is slowly rusting out by continuing to get what? Regular oil changes, changing your tires when the treading is low, switching your wiper blades when they've broken down. Yes, you can slow down degeneration, but you can't stop it. And so beneficial mutations don't work. These types of compensating mutations don't work. Synergistic epistasis doesn't work. Snake can clarify, but I believe these types of compensating mutations apply to the mechanism of synergistic epistasis. Now, waiting for a single desirable beneficial mutation, while many thousands to millions of deleterious mutations are accumulating in all sorts of nucleotide sites, only increases fitness in a very narrow sense. But absolute functionality always goes down. And so a narrow increase in fitness or a localized episode of compensation that Taylor here is pointing to only results in a shrinking functional genome size, as we've seen in Lenski's bacteria. And all of this has been looked at in Mendel's accountant, highly sophisticated program that... Thank you. Highly sophisticated program, basically, that Taylor spent some time rebutting. And these results have been published in secular journals. Okay, they haven't been refuted. Mendel's accountant is user specific, as in you can input whatever settings you want. They can be realistic or unrealistic. And whenever you input realistic conditions, evolution fails and genetic degeneration is inevitable. And so what they've done through this program is they've been generous, way more beneficial mutations than is realistic. They've run simulations with intense selection applied. And yet genetic degeneration, guess what? It still occurs. It's still inevitable. Okay. Another thing he said, that it's a contradiction. I've got a minute here. He said it's a contradiction to say mutations are nearly neutral, unselectable, and also deleterious. No, it's not a contradiction, because it just means that they are not detrimental enough to kill the organism. And that's where we have to get into absolute fitness versus reproductive fitness. Okay. Let's say I'm hit with a mutation that decreases my lifespan by 15 years. Okay. Well, that's an example of a reduction in my absolute fitness or total functionality. But in terms of reproductive fitness, it doesn't do much, because I can still have kids. I can still pass on my genes. And there are a lot of mutations that result in disease that are degenerative, but they're not big enough to stop that organism from reproducing. And that's why the major problem has to do with the low impact mutations. And I don't believe Taylor is adequately dealing with those. And that's 8 minutes. So I yield.
Actually, it was perfect timing there, SFT. Thank you so much for your rebuttal. We'll hand it off to Taylor now for his 8-minute rebuttal. And whenever you're ready, go ahead, Taylor.
Oh, I think you're
Might be on
muted,
mute.
Taylor.
Yeah.
You're right. All right. Okay, so you claimed a few times that there's a general trend towards degeneration, but there's actually no data to back that up, other than Mendel's accountant, which never I've read multiples of his published papers. I've all the ones that I could find were just published through ICR, that was Creationist journals. And he never uses realistic conditions. And unlike computer programs, which you can design to have the effects that you basically want, in real life, we don't observe genetic entropy at all. In fact, we observe higher fitness in organisms like the salmonella that I brought up. It adapted, it had a hit to fitness, and then it adapted again, and then it was more fit than it was when it started. And we can go into that, and I can show you the quotations later. But that all empirical evidence is showing that what Sanford is saying is impossible is actually observed in real life in actual organisms, not computer code. So there must be a problem with the user or the code if it's giving results that contradict reality. So there's about, I know you said there's 100 mutations per cycle. There's about 124, but only 4 of them are actually deleterious. Most of them are nearly neutral or compensatory. And no, compensatory mutations are not synonymous with epistasis, but compensatory mutations can work with epistasis. So Kimura was not studying deleterious mutation accumulation specifically. He was actually studying neutral selection. So he did mention it, but the only thing that he assumed was that there were likely going to be bottlenecks that occurred. He didn't assume that that beneficial mutations got rid of the problem. He actually calculated that, and they do. They just do it way too well for realistic models. So that's why he left it out, is because if you add in even a small amount of beneficial mutations, according to Kimura's models, it gets rid of the problem of slightly deleterious mutation accumulation. And so if you're constantly accumulating slightly deleterious or neutral mutations, which there are some purely neutral mutations, they're called synonymous mutations, and they're purely neutral because they give the same amino acid. The protein is going to be the same. So next example, I guess, Lenski doesn't show genetic entropy. Just because the bacteria are losing genes doesn't mean that they're losing fitness. They're adapting to a different environment. But again, the salmonella bacteria experiments, they show that they actually get more fit after mutation. And the Lenski bacteria are fine. They're not degrading. They're just, the parts that they're losing are not necessary. So that's why they're losing it. And so that there's no connection there to genetic entropy. I never mentioned sickle cell, but the thing that I mentioned was about hemoglobin was not about sickle cell. It was about the effects of compensatory mutations and how likely it is for a compensatory mutation to fix a protein. And it also shows the anti-fragility of proteins and genes, where there are multiple fixes to one problem. And there was one experiment where they showed there were 9 fixes to each problem about. And also on the subject of sickle cell, heterozygous sickle cell actually has healthy cells, but retain some immunity to malaria. So that actually is a beneficial mutation. So yeah, but I'm not sure where the numbers you're getting are, where you're saying that there's no way that compensatory mutations can fix the problem. You'd have to actually calculate that. In actual living models, it does. So we don't have perfect models of this. We don't know exactly why it happens, but pointing that out is not actually a defeater, because we can observe populations that actually go through the opposite of genetic entropy, which is an actual preclusionary defeater for genetic entropy. So we observe that populations are able to get over genetic entropy. We don't quite know how to mathematically model it perfectly. That's not a defeater. So beneficial mutations are rare, but you don't need many of them. And you can have a ratio highly in favor of deleterious mutations because they're all being taken out of the population. In fact, the majority of them are of the worst ones are already taken out of the population before you're even born. Gametes get the brunt of the worst ones that don't end up fertilized. So, yeah, I guess I would like to know why you claim compensatory mutations won't solve the problem. I'd like to see the math. And talking about the operation, the contradiction that I mentioned earlier, it is a problem because if these are slightly deleterious and accumulating, they should be slowly becoming selectable. And due to epistasis, some mixtures become more selectable than others. And during this whole time, you're also getting compensatory mutations. And so different mixtures are giving you working mixtures, and you're getting, on top of that, compensatory mutations. And on top of that, beneficial mutations being rare will also compensate, and you don't need many of them in the models. And basic selection and recombination gets rid of the majority of the deleterious mutations. And so most of them remain neutral, effectively neutral. And they'll remain that way. And as soon as the population approaches that threshold where you have most or half of your genes are replaced with mutations or deleterious mutations, they definitely become selectable. And that's where the mutation selection balance is because around that threshold, you're going to have some mutations that bring you back towards fitness and some mutations that bring you towards less fitness. And if you cross that threshold, those are selected out. And again, if you have mostly mutations at that point, then it becomes more likely, once a gene has already been mutated, it's more likely that the next mutation is actually going to fix it or give it some sort of beneficial interaction or compensation. And this has been modeled and has been observed in model organisms. And all of the data that Sanford and folks can come up with is actually, all it is just some computer models. They don't have any actual empirical data which fits the computer models.
Wrap it up.
I'm done.
Awesome. So that ends the individual portion of this debate tonight. We're going to go into the shared portion where both of you guys will have an open discussion. It'll be 50 minutes long. We'll just let natural, free-flowing discussion. We'll let SFT begin the discussion here, and we'll just keep it going.
Okay, thank you, Praise. Thank you, Snake. So many points. It's almost like we need another rebuttal, but hopefully we'll be able to touch on all of them. So I'll try and pick one of the many. I appreciate your opening and your rebuttal. Appreciate you looking into this for this debate. You mentioned beneficial mutations, synonymous mutations. I definitely want to discuss, but it seems like you're really hung up on your mutations that supposedly compensate for the degeneration. But you did mention You said more or less, if they are slightly deleterious and accumulating, then they should by definition slowly become selectable. And then when you bring in synergistic epistasis, some become more selectable than others. So I guess my first question to you would be, is your slightly deleterious mutations, and I provided several citations, for example, one from Kitely, Michael Lynch, and Peter D., where they pointed out that the vast majority of mutations are deleterious. And this is well established. This is one of the most well established principles of evolutionary genetics. And then we also had Kitely point out that it seems unlikely that any mutation is truly neutral in the sense that it has no effect on fitness. So the point is, your detrimental mutations, yes, they're high impact. Selection can see them. There's no reproduction. Selection has to do with the death of individuals, right? So let me circle back to my basic question. So yes, mutations can accumulate that are low impact. They're only slightly deleterious, like a single spelling mistake in a book the size of an encyclopedia, let's say. On their own, they're inconsequential. But as they build up over time, they become a problem. And so my direct question to what you said there has to do with the fact that by the time these mutations build up in a population to where they do become noticeable, it's a type of mutation count mechanism in a way, or some have called it carrying capacity. By the time enough mutations have accumulated in that population, that entire population is multiply mutant. And so selection's limited. How do you deal with that, Taylor? The fact that your entire population would be mutant. And so you're basically just picking, selection's basically just picking between more mutant, some a little less mutant, but nonetheless, every single individual in that population has accumulated mutations and are therefore more mutant than their parents, than their grandparents. Go ahead, take your time.
So you're starting off with the assumption that we started off with some sort of perfect genome, whereas you could pick any point in time and it's actually going to it's all mutant. So the question being why, sorry, what was the question again?
Well, with what you said, I think is a major issue because, yes, as I pointed out in my opening, the evolutionary model would suggest that all DNA variation, all DNA diversity for the most part is the result of mutations over time. But in real time today, I mean, we have famous geneticists like Crow and Lynch that concluded humans are degenerating at a rate of between 1% to 5% fitness each generation. So yeah, you would look back to ancestors over millions of years, and those DNA differences have always been due to mutations. But if today we see those mutations are mostly deleterious, disease-causing, damaging, then how could you look to all the variation in the genome and say, well, that's been built up over millions of years of evolutionary process? No, because the mutations put shelf lives on genomes in the first place. If you want, but feel free to respond to that.
Well, there's no evidence of that. So if you take humans, for example, we could be degenerating. It doesn't actually matter because we have very little selection. So we're not a good evolutionary model because we've effectively cut out selection from our populations. I'm looking for, there was a study, the X chromosome and rate of deleterious mutations in humans. This found that there was about 4 deleterious mutations per human zygote. So that might contradict your citations a little bit, but that is just deleterious, not slightly deleterious. So we can focus on how slightly deleterious mutations are selected. You claim they're not selectable by compensatory mutations or by, well, they're not fixable by compensatory mutation. They're not selectable by epistasis. So the argument would essentially be, well, would you agree that it is selectable by epistasis, but you're saying that everything in the selection pool has these mutations in it, so it doesn't matter.
Right. So basically, because we have an increasing genetic load and everybody is therefore multiply mutant. I mean, take every single person on the planet today, 7 to 8 billion people. Every single person has accumulated roughly 100 new mutations per person, per individual. That means every living person would be more mutant than their parents, more mutant than their grandparents. And so the problem is selection, it can't sort out the good, the bad, and let's say the ugly. It's limited because every chromosome has this complex array of nearly neutral and deleterious mutations. And the reason why they are called nearly neutral is because they're very, very slightly deleterious, but yet still unselectable. And so they're subject to genetic drift and they spread, they degenerate. So for you to say that these compensating mutations, compensatory mutations, can counterbalance the damage, well, how's that the fact when the entire population as a whole has this complex array of these deleterious mutations, Snake?
Well, I mean, Kimura and Kondrashov have produced calculations that show that a certain amount of beneficial mutations can effectively outweigh the deleterious ones, and you need a very small amount.
Which paper did they show that in?
Let me find Kondrashov, Muller's ratchet under epistatic selection, and the Kimura paper. I mean, it's the one Sanford cites. I forget what it's called.
So he said beneficial mutations will be able to counterbalance the damage done by the nearly neutral mutations.
He said that epistasis can effectively halt it.
So epistasis, I guess for the audience sake, what do you mean by synergistic epistasis? Basically, these mutations accumulate, they're deleterious, but eventually they start amplifying each other's effects. And so selection's able to see the most degenerate, essentially, and then remove them from the equation. Is that what you mean by synergistic epistasis?
Yeah, and it's not the only selective pressure. So there's other things. There's recombination, which I don't know if I mentioned. I meant to mention it. That is...
I got that right.
A driver of diversity. So mutation isn't a driver of evolution, it's a driver of diversity. You got to combine that with selection. But mutation isn't the only driver of diversity either. So recombination, which itself helps get rid of mutations, deleterious mutations. It also helps with the synergistic epistasis.
Let's deal with each at a time.
We have synergistic. I'm going back to where I started.
Okay.
Synergistic epistasis, basically, it can get rid of a lot of this deleterious stuff. So when you add that to other forms of selection, I'm just wondering, where is the math that's saying that that's not possible?
Okay, so let's start right at the beginning. Firstly, again, I just want to point out the fact that we have these evolutionary population geneticists that agree. They're pointing out that all mutations are deleterious, and it is
not all. No.
Well, the quote that I had was, I'll pull it up again. So it's going to depend on your assumptions of junk DNA as well, because a lot of your evolutionary population geneticists, they're assuming that the vast majority of the genome is junk. I've heard some say, well, about 10% is functional, 90% is junk. And so most of your neutral mutations are therefore hitting junk regions and they're not really doing any harm. But even if, and it's not just creationists that have pointed this out, and there's a lot of points on the table, so let me just try and address a few, and then you take your time. Even if the mutation rate was 1 to 5 per generation, as in the genome's only, let's say, 5% functional, that's still roughly 5 deleterious mutations that are accumulating every single generation. And that means even the most fit individuals are still going to be more mutant than their parents and their grandparents. So if the genome's 80% functional, 50% functional, well, then that's 50 deleterious mutations, 80% deleterious mutations. And so I'd like to point out that it's kind of arbitrary to even ask who is the most mutant. since I think this goes back to the fact that the entire population has accumulated mutations from previous generations. And so if the entire population is multiply mutant, let's deal with synergistic epistasis for now. Basically, if we have lots of mutations that are deleterious, these deleterious mutations accumulate and they amplify each other's deleterious effects. And so now we have a level of degeneration that's so intense that selection is now more efficient. But think about it logically. You introduce synergistic epistasis, and now you have a population of, let's say, 7 to 8 billion people. Everybody's multiply mutant. And now we have some that are slightly more mutant than other mutants because the effects are being amplified. And so selections drives a subpopulation into extinction, removes them from the equation. Again, isn't that only going to slow down the degeneration, since the individuals that have not been removed from the equation through synergistic epistasis, they are still more mutant than the generation before it. And so mutations still accumulate from generation to generation. Does that make sense, Snake? And feel free to speak to those points a little bit.
Yeah. So the population being mutant isn't actually a problem. In fact, it's assumed that every gene is a mutant. So we get rid of the worst of the worst with things like a synergistic epistasis makes negative selection more active on certain mixtures of mutations. So we get rid of the worst of the worst, but there's still a lot of other forms of selection left to get rid of what's left, which is just slightly deleterious effects. So, and that's been modeled, and a small amount of beneficial mutations will override the majority of deleterious mutations. And one of the reasons is because they don't have fixed effects. So if mutation A is deleterious, then but mutation B is also deleterious, but sometimes A plus B is beneficial. That's just the way it works sometimes. There was a flu mutation experiment done and it was the exact same effect that I just described. So like mutation A, I forget what it's called, but there was a mutation they were studying in it, and it hit the fitness very hard. And but there was another mutation that they saw that popped up that when it was combined with mutation A that was really unhealthy for the flu, it then had greater fitness than the original flu that they began studying.
If I could, is this partly what you mean by compensatory mutations, where you have mutation A is deleterious, mutation B is deleterious, but mutation A and B together creates a benefit or a compensation to the overall loss? Can you define your terms a little bit? Is that what you mean by compensatory mutations? Or if not, what do you mean exactly by that term?
Well, in that context, yeah. So the mutation effect is context dependent. So you can have a compensatory mutation, which is literally a fix to like a broken gene, or you can have a compensatory mutation that just interacts with another gene in a certain way.
Would that be like a back mutation? So would a back mutation be a mutation that compensates?
Yeah, but that's much more rare than a general compensatory mutation that fixes it in some other way. So if, for example, like one mutation decreases the secretion of some chemical, but another mutation amplifies it, that would be compensatory.
But isn't that example of a compensatory mutation, isn't that a beneficial mutation then?
Oh, yeah.
Okay, well, but the problem in general is your beneficial mutations, your compensatory mutations are rare, Lenski's experiment demonstrated that they're about 1 in a million. And for sake of argument, I can give you a few truly beneficial mutations, but there's plenty of literature out there anyways demonstrating that a lot of these beneficial mutations pop up and they're reductive. And so what you have here basically is your entire genome being hit at all sorts of nucleotide sites with these nearly neutral mutations. And then you've got a few rare beneficial mutations arising. And therefore, these mutations are only going to increase fitness in a very isolated manner. And so these increases in fitness you're talking about, let's say you've got, as you pointed out, mutation A, deleterious, mutation B, deleterious, but both of them side by side is some kind of benefit. Well, that's just going to be a very localized increase in fitness. But overall, what do you have? Well, we have what we see in Lenski's experiment is we have shrinking functional genome sizes where you've got a few nucleotide sites that are improved, but then you still have this great multitude of sites being degraded. And so where is the absolute compensation? Where is compensation that's not just localized, Snake, would be my question. Where is the universal compensation? As in, I want you to address what I believe is the key issue, which would be a net gain versus net loss. Go ahead.
So a net would be an accumulation of individual circumstances. So what that's not taking into account is that there aren't fixed effects. So epistasis effects wouldn't be counted necessarily as a beneficial mutation in these numbers because it's context dependent. So
right.
It could be deleterious in one person and beneficial in another person. And so it's kind of a numbers game. So there's what's the experiment? It was another flu, I think. Basically the average fitness of the population, it was a bacteriophage. They overloaded it with mutagens. So they mutated every single possible genome or space in the genome that they could. And it still survived. The average fitness declined, but the maximum fitness increased. So there were some individuals in the population that were created, a small number, that were actually more fit than the original, even though most of the ones that were produced were less fit. So that's what Kimura is talking about when he says bottlenecks will actually fix this. So if you have a bottleneck to that population, all of the average fitness ones are cut out, and now you have the minority of them, or they used to be in the minority. Now the majority are now higher maximum and average fitness if you apply a bottleneck to that.
Okay, but let's take the human population, for example, 7 to 8 billion people. Are you trying to say to solve this problem of genetic degeneration, which I'd like to just read a couple quotes and get your thoughts. Kondrashov, for example, in his paper, Contamination of the Genome by Very Slightly Deleterious Mutations. That's what I'm talking about here. Why have we not died 100 times over? And he says, I interpret the results in terms of the whole genome and show in agreement with Tachida that very slightly deleterious mutations can cause too high of a mutation load, and it acts like a time bomb. But to corroborate that, we have him pointing out that in the average human genotype, over 100 genes are dysfunctional or altogether missing, and over 1,000 genes are substantially impaired. And here's the last quote I want to go over. It has to do with Higgins and Lynch. And they talk about how, actually, this one's just Michael Lynch. He says, in the United States, the incidences of a variety of afflictions, including autism, male infertility, asthma, immune system disorders, diabetes, all of these mutation-related diseases are on the rise. A lot of it has to do with epigenetic and environment, I understand. So we have these population geneticists that are acknowledging that Mutations are accumulating in the human population, in the human genome. Diseases are skyrocketing. Cancers are skyrocketing. So are you saying that basically the human population now at 7 to 8 billion needs to experience this massive population reducing bottleneck in order to save the day?
If you're suggesting some kind of eugenics program, I'm not suggesting that
I'm
at
just
all.
saying. Okay, so
But
what would save the day then?
So this whole thing does require selection, but
Right.
it's not genetic entropy unless it's inevitable. So if it's just humans who are accumulating these things because they don't have selection anymore, then sure, that's not a problem for the idea of evolution. It is a problem for us, but this isn't happening universally. So it may be the case that our medical technology can keep up with the mutations. Like our technology is the compensation. So if we're, I don't know, if our skin starts falling off, but we invent a lotion that stops it, it's not a problem. But at some point, if it gets too bad, there will be a mass dying and a bottleneck. And like I was talking about with the bacteriophage, there will be certain individuals that, due to recombination, due to their synergistic epistasis, and due to getting lucky by inheriting some of the beneficial mutations, there are going to be some individuals who are on not suffering the same mutations as everyone else in the population. They'll go on and kind of the whole cycle will restart again. So unless the population's like under 1,000, in which case mutational meltdown is a problem. But again, it's not genetic entropy unless it's inevitable in all cases. I don't know if you muted or not, but
right, I was muted.
I
Sorry.
can keep going.
So I'll reiterate what I was
keep
saying.
talking.
I was talking to myself. So,
Yeah.
I could point to a number. I want to stick with humans for now, but I could point to a number of isolated cases of what I call microgenetic entropy, where we've got these isolated butterfly populations. They've degenerated significantly. Polar bears, cheetahs, your hominid fossil record, you could say, with Neanderthals, Hobbit, Floresiensis, Erectus. Mammoth populations have experienced mutational meltdown. Now, these are examples of small inbred populations where genetic degeneration accelerates. These deleterious mutations that are in recessive form come to the forefront and lead to rapid genetic meltdown. Now, in a large population, though, one could say, and as you evolutionists love, micro versus macro, we've got macro genetic entropy where, as more mutations accumulate, your 100 new mutations per person per generation, we now have over time more recessive spots in the genome where we now have what? More homozygous genetic loci. We've got the potential for more deleterious recessive mutations to come to the forefront. And so it may take a longer time with larger populations, but that noise is still there. As a matter of fact, that noise is worse in larger populations. And so a larger population is going to take longer, but to answer your main point is it is inevitable, because let's say we've got 7 to 8 billion people on the planet. If you were to, not through eugenics, but let's just say selection was intense and it was able to remove the most mutant. Because remember, the problem is your low impacts. The fact that every generation is going to be slightly worse than your previous generation. And so selection, for sake of argument, could remove 50% of the worst mutants, since we're all multiply mutant. And so now you're left with, let's say, 4 billion people. Has that solved the problem with this intense selection? No, because you have 4 billion people. Although you've removed your most mutants, you're still left with 4 billion people that are more mutant than the generation before it. And so I would argue, yes, it is inevitable, but there are means where degeneration can be slowed, but it can never be, even if you had this massive population bottleneck that reduced the population to 10,000. Well, there's an example with your cheetahs. They're down to 7,000. And conservationists are incredibly worried about them. Their sperms degenerate. They got all these deleterious mutations and diseases that have been manifested. I don't see how that's now you're just left with a population that's small, and now they're going to be inbred until they grow in numbers. And so I guess basically I just don't see how the mechanisms you've proposed so far are going to solve the problem. Here's the last thing I'll say: synergistic epistasis. I'm just looking at my notes. I want to address everything before we move on. Synergistic epistasis is just going to speed up the degeneration process, since again, everybody's multiply mutant. And now you have, let's say, this subgroup where their deleterious effects are amplified because you have all of these epistatic interactions going on. Okay, so selection removes that group from the equation, but everybody else is still mutant. And so the problem persists, is my point. Go ahead.
So epistasis would just get rid of the worst mutants. So then you have stuff that's left over that's, you know, maybe every once in a while you purge it and the car is still rusty, but it's not falling apart. So the accumulation is kind of a misnomer because they don't have fixed effects. If one generation accumulates, 4 or 5 deleterious mutations, the next generation of mutations might have a good effect on that. And so basically, like, you would be looking at something like over a long period of time, people might have bad knees, but their eyesight gets better overall. So it's the deleterious effects kind of migrate in that way, because while you're accumulating more, you're also having those ones from a couple generations back getting fixed and compensated for at the same time. So the effect of a mutation or a gene does not stay stable over time, and this is one of the things that Sanford doesn't account for, and certain other models do. And I should explain Kondrashov's Why Haven't We Died 100 Times Over a little bit more. He did a model that said that selection working on mutations independently has too high a mutation load. And so he considered several models. Synergistic epistasis was one of those ones that saved the populations. We don't know for sure if that math is exactly modeling reality, but it can mathematically overcome it. But it's called a paradox because some of the math is hard to do, but in reality, we don't see what some of the very simple math is trying to say.
Have you read the paper? Because Dr. Sanford's resume is available. He's got, I believe, over 140 publications. He's published numerous times in the secular journal, papers that have been read by over 10,000 scientists with no serious critique, at least in the secular literature, using Mendel's program. And so I've got a whole slew of them in my book and my presentations. Here's just one specifically from a secular journal, and it's titled Mendel's Accountant, a biologically realistic forward time population genetics program. And in these papers, they talk about all the different parameters. They talk about in detail how you can set realistic conditions, unrealistic conditions, this amount of selection, this amount of beneficial mutations. They account for recombination. And these papers are published, and I don't see any serious critiques of them other than in some blogs or maybe some YouTube videos somewhere out there by some evolutionists. And so I guess my question is, where's the real serious critiques then of these thousands of numerical simulations that have been done, and they've looked at beneficial mutation. They've looked at super beneficial mutations. They've looked at synergistic epistasis. They've looked at all types of mutation count mechanisms, and genetic degeneration is always inevitable. Even at the National Institute for Health that Dr. John Sanford spoke at, clearly not a young earth creationist organization, in his hour-and-a-half lecture, he went through all of these numbers of papers, some through non-secular journals, others through secular journals, basically backing up what I'm saying here, that these mechanisms, they've been analyzed and they've been falsified. So I guess basically my question to you is, have you read any of these papers on Mendel's accountant, and where are the real serious critiques of them, including your H1N1 paper as well, which is published in a secular journal? Go ahead.
Well, like I said, it was published in a computing journal, not a biology journal. So the one you just brought up, the Biologically Realistic Forward Time Population Genetics Program, right?
Right.
That's published in Scalable Computing. And so they're not looking at any biologically realistic constraints. They're just looking at, does your program work? Like,
well, and
does it crash the computer or whatever, you know?
Well, what about the papers that deal with things like selection, beneficial mutation, synergistic epistasis?
Yeah, so the synergistic epistasis one I know is not published in any secular journal. And it specifically sets beneficial mutations to 0 and restricts the population to 1,000. So that's the dangerous range for inbreeding. And
is that the waiting time problem paper, or the synergistic epistasis one?
That's the synergistic epistasis.
Okay.
Yeah.
Okay. Well, even without going into the details on let's just say the synergistic epistasis paper, I think it just goes back to logic on that, which I said earlier, is where you've got, let's say, even very strong synergistic epistasis. How in the world is it going to curb deleterious mutation accumulation? Logically, it would accelerate it, because you just have subgroups apparently where the deleterious mutations that they've accumulated, they are amplified, and now selection's more efficient and removes that group from the equation. Okay, so now you have that group that's just experienced rapid extinction, and you're left with everybody else that still has a lot of, see, selection's limited because it can't remove every single person on the planet. It can't remove all 7 billion. I should say this for a clarifying question, Snake. So do you look at the reason for the citations that I've provided with genetic degeneration and the increases in your genetic related diseases in the human population that Michael Lynch talks about, Kondrashov, Kitely, so on and so forth? Do you look at that as being, it doesn't sound like you're denying it, but do you look to relax selection as being an explanation for human genetic degeneration, Taylor?
And gentlemen, I'm just going to jump in here really quick, just to let you guys know, within the last 10 minutes of the open discussion, it's been an enthralling discussion. So just let you guys know about, we're in the last 10 minutes.
Okay, let me say this before you respond, Taylor. I'll be listening. I got to run away from the computer for about 30 seconds. But I'll give you the last word on this specific topic of compensatory mutations and synergistic epistasis and whatnot. And then I'd really like to move into, because time is flying by, I'm looking at everything I've written down. I'd love to talk about synonymous mutations as they apply to genetic entropy as well. So feel free, take your time to respond to what I said. I'll be listening.
So yeah, that's certainly a possible explanation, is relaxed selection is bad for mutation accumulation. And as far as selection goes, no one proposes that any form of selection can purge all mutations. It is a balance where you're constantly accruing more mutations, and you never have a perfect genome. You always have some problems. Everyone's got a thing, you got a mole on your back, or you got bad knees or bad eyes. But your kids might not have those problems because you're recombining your genes with whoever you're getting nasty with. But so epistasis only removes the worst of the worst. And then there's other forms that deal with what's left. But again, there's no proposed mechanism that says this selection sweep will get rid of all deleterious mutations and you'll have a perfect genome. That's not a thing. So the problem is, it's called the Kondrashov calls it a paradox, because while some of the math suggests that there's a problem with accumulating mutations, there is math that solves that. But he calls it a paradox because in reality, in real populations, we don't see the inevitable degeneration. In fact, we see the opposite in many cases, which shouldn't be possible if genetic entropy was true.
Okay. So you said something there that I've got in my notes too that you've brought up that we haven't touched on. Okay, so recombination, for example. I remember when I debated Dr. Stephan Frello a few years ago, his main mechanism to solve genetic degeneration is recombination as well. But the issue I have with that is, yes, recombination can break a lot of these deleterious alleles up, and we can get new chromosomal combinations that can be beneficial. Even from our starting point, created heterozygosity, we would. And one thing I want to say too, because I think what's being ignored here as well is fixation. And right now we exist in a population that's 7 to 8 billion. So fixation's rare. Okay. But you do have just all of these deleterious mutations that are floating around. If it's a smaller population, you've got rapid fixation. And in general, over a long enough period of time, your per generation rate will equal a fixation rate. But in these smaller populations, let's say you did have a bottleneck, you would have faster rates of fixation, and fixation speeds up the issue. But when it comes to recombination, although recombination can break up a lot of these deleterious alleles, it seems to be, for the most part, other than when we look to gene conversion, but recombination appears to occur mostly between genes rather than between nucleotides. Gene conversion is interesting because it looks like it can break up your single nucleotides. But recombination itself would tell us that within any local gene sequence, for the most part, there's basically no recombination. And this goes back to what some have dubbed as being Muller's ratchet, okay? And so what I'm trying to say is, if we have all these good mutations and then we've got all these harmful mutations, these slightly deleterious mutations that have accumulated, okay? But you've got these bad mutations linked with maybe a couple rare good mutations, but they can't be separated because of the limitations of recombination. So you got these massive linkage blocks, you know, some 10,000, 30,000 letters long. And since you don't really have much recombination going on within those genes to break up those deleterious alleles, then all we get is those linkage blocks becoming worse and worse over time, where these linkage groups are reducing in fitness continuously, even though you might have recombination. Again, I don't think it's addressing the key issue. And the key issue has to do with counterbalance, not localized increases in fitness, or, you know, a localized example of a beneficial mutation where you get this single desirable mutation at this nucleotide site. Everywhere else is still degenerating. Here's the last thing I want to say. A lot of this is technical. For the audience sake, if I apply it to a car, and you mentioned this earlier in terms of an analogy, I have a car, get it right off the, you know, the assembly line. It's working great. That car is not going to last forever. It's going to accumulate rust. That rust is mostly going to accumulate unnoticeably. Now, if I'm good with my car and I'm doing the right things, I should be doing oil changes regularly, changing the tires when the treading is low, changing the wiper blades, not driving on empty all the time, you know, driving it responsibly. But regardless, even though I have these localized improvements, based on the way I treat the car, it's still going to rust out over time. And I find, here's the last thing I'll say, Taylor, because I know you're dying to refute me here, but recombination, synergistic epistasis, compensatory mutations, it's all just localized examples of improvement. But universally, it's still overall degeneration. So I said a lot there. Go ahead, take your time.
So yeah, recombination can straight up just get rid of the worst ones. But over millions of people, you're going to have some children who have combinations and recombinations that would only carry like the fresh mutations. So that's how you can look at it, is they have combinations that only carry the freshest of mutations. So they're getting rid of the old ones that have accumulated. They're getting new ones, but they're also getting rid of the old ones. So there's a study too, I mentioned. It's quantifying the threat of extinction from Muller's ratchet in the diploid Amazon molly. They have they're non-recombining. So they actually solved mathematically how they can, one possibility of how they're surviving and not having mutational meltdown. That was solved with compensatory mutations. So it's not just recombination. It's not just epistasis. It's not just compensatory mutations. They're all acting together, and together it creates a universal effect. And like the example with the salmonella bacteria that actually, due to compensatory mutations, ended up more fit than they started with. This is an actual, this is why they call it a paradox, because we actually observe that these populations are not suffering from the effects of mutation accumulation. In fact, they're getting better in a lot of circumstances, and that is a preclusionary fact to genetic entropy.
But it, again, to me, it seems like we're not necessarily dealing here with the low impact mutations that are accumulating. This goes back to earlier relaxed selection in the human population, where because of relaxed selection, we in humans, for example, more high impact mutations are making their way into the next generations, right? In the wild, you have a zebra that's born with a big mutation. Let's say one leg shorter than the others. Well, selection is going to remove that mutant from the equation because the lion is going to seek out the mutant zebra first. He's going to be dinner. But if that same mutation occurred in humans, well, because of relaxed selection, we take care of each other, medical advancements, improvements, you know, you're talking about that earlier. Okay, fine. That high impact mutant thrives, survives, still has kids. But again, it's not the issue. The issue is the low impact mutations, those that are unselectable, those that selection can't see. And, you know, you've mentioned some mathematical models. I would definitely like to see those. But from my understanding, what's been proposed by people like Kondrashov, Lynch, Kitely is, for one, relaxed selection. Well, you know, humans are degenerating because of relaxed selection. I feel it ignores the low impact mutation, synergistic epistasis, as you've talked about. But again, I feel that ignores the bigger picture. It ignores the low impact mutations. Real examples rather than just hypotheticals. Lenski's experiment. You know, you pointed out earlier in rebuttal, and feel free to respond, that, well, you know, they're doing just fine with these localized increases in fitness, but they're losing genes. They've shrunken functional genome sizes. They're worse off than their ancestors. So how do you see that as something that has universally increased total functionality? Yeah, in that very narrow artificial environment, maybe they're doing okay. But the second they move to another environment, I mean, that's it. They've degenerated. They've lost so many genes, and those genes that have been lost, they're not going to come back. And so this is an example of reductive evolution. So I would argue we see genomic decay even in bacteria. That's a real-time example, not just hypotheticals, not just stories. I'm not sure if I addressed your point there. There's quite a few there, but go ahead. Feel free to respond.
Well, they're not necessarily worse off. The Lenski bacteria are perfectly adapted for their environment, but the other bacteria I've mentioned several times, it was a Salmonella experiment. Let me see if I can. Compensatory adaptation to the deleterious effect of antibiotic resistance in Salmonella typhimurium.
What's the benefit there?
So what it goes through the fitness peaks and valleys effect that I talked about. So we observe low impact fitness hits often to mutations, and then we witness compensation where then the fitness goes back up, and it goes up and it goes down. And
yeah, but how common is the compensation is the point I've been making. It's pretty rare. Like a beneficial, it's not like it's always, see, we just got, I'm sorry, go ahead.
It's common enough to observe it in real time in populations.
Well, we've observed so-called beneficial I'd argue they're reductive and functionally compromised, but nonetheless, in Lenski's experiment, it was 1 in a million. That's pretty rare, especially when every generation go ahead.
I mean, the bacteria produce millions of each other per day, but
well, what's the beneficial mutation rate in humans then?
Even if there's like a 10-to-1 ratio of deleterious to compensatory, there's 10-to-1 compensatories that can fix any single deleterious. So if there are fewer compensatory mutations per deleterious one, each single compensatory mutation is able to fix multiple has the probability to fix multiples of them have the probability to fix the single deleterious that we're looking at. And we observe this experimentally that it does happen with enough frequency.
Okay, but assuming what deleterious mutation rate? 1 per generation, 10, 50, 100? What's this math based on?
Well, it's with this experiment, it's not math. It's not a model or a program. It's literally just breeding bacteria, and they're actually getting more fit. So right, the mutation which caused antibiotic resistance lowered its fitness in several areas, but then subsequent
you got some background noise, Praise.
Yeah, subsequent mutations ameliorated those costs, and they kept the antibiotic resistance. So the damage done by the antibiotic resistance mutation was compensated for by it says at least 35 different amino acid substitutions.
But what I've seen from a lot of these mathematical models and explanations is, firstly, there's population geneticists that have pointed out that 1 mutation per generation could be too much. And that's what a lot of these mathematical assumption or models are assuming is 1 mutation, maybe 5. And this is where it gets into a whole nother conversation I think we need to have on this podcast, is what amount of the genome is functional. Because if the genome is, let's say, 80% functional and 80 of these mutations are deleterious, well, then there's no compensation. That's going to counterbalance that damage. If you're dealing with 1 that's deleterious or 2 or 3, I would say it's still a problem. But that, and correct me if I'm wrong, that is what these mathematical models are based off of. Go ahead.
Yeah. So what's getting compensated for is what's left, the least deleterious mutations and the deleterious mutations that survived other forms of selection. And 1 per generation would be too much if we didn't have all those forms of selection and if we assume fixed fitness effects. So in that Salmonella experiment,
fitness effects, are you just saying there's relative fitness in the population?
No. So in the Salmonella experiment, there was a mutation,
right,
which gave them antibiotic resistance. It still has that mutation, but it doesn't have the same effect as it originally had, because now it has epistatic effects with
Okay,
other
so
mutations.
okay, so one mutation in the genome that was pre-existing is interacting with this new mutation that you're saying is beneficial, and so it's having a positive effect, a compensating effect, basically.
Yeah.
Okay, so again, if, and my major problem with this is increasing fitness in the absolute sense, not just these localized examples, a narrow increase in fitness. That is where the issue lies, because these isolated examples of compensation or rare beneficial mutation, you mentioned sickle cell anemia. I originally mentioned sickle cell anemia, but that you commented on it. That is an example of, and I know Prey said there's only 5 minutes left. So let me say this, and I do want to get into the synonymous mutations. Because it does come down to how functional is the genome. But nonetheless, something like sickle cell anemia, I mean, it has a localized benefit. It has a very narrow advantage, one could say. But nonetheless,
yeah, but that can happen to each effect that's damaging enough. So most of it's going to be neutral and not selectable, but some effects are going to break through the haze of nearly neutrals, and those are more likely to be compensated for.
So you basically are saying there's a trade-off then with your compensating mutations and your low impact mutations that are truly deleterious.
There can be, but in this specific example, and there was a flu example as well, where they took a temporary fitness hit, but then with more mutations accumulating, they actually got more fit than they were originally.
Do we see this in humans? Because humans, every single generation, how would you answer the question? Are humans presently getting better? Or would you agree with people like Lynch that would say that, we're losing 1 to 5% fitness per generation?
It depends how you're measuring fitness, but sure, I can concede that, but it doesn't actually help the case of genetic entropy, because genetic entropy needs to be universal, and we're actually seeing the opposite of genetic entropy in many populations, which is preclusionary.
Yeah, but it looks like your examples, correct me if I'm wrong, are viruses and bacteria. Where do we see this in the wild with higher, longer lived mammals like elephants, humans, whales, lions?
The Amazon molly, the non-recombining fish that I talked about, does not go through genetic entropy, and they quantified that. But the reason,
well, send me that paper about the fish. I'd like to see that.
Yeah, and mice and other model organisms is because they have a fast generation time. We can't study humans like that because the scientists studying it will be dead by the next generation.
Well, I just put out a 17-page article, because we are running low, where it's literally titled, and it is available on the website, "Can Simple Organisms Overcome Genetic Entropy?" I get into mice, as you just brought up. I get into bacteria. So maybe we can have a part 2, since as we are winding down. Yeah. I do want to give us 5 more minutes, because I'm looking at my notes here: compensatory mutations, Mendel's accountant, beneficial mutations, synergistic epistasis. We've basically discussed every point except for synonymous mutations. And so I would argue, and I'd be curious as to your thoughts, Snake, is, and for the audience, basically what we're talking about here is basic genetics, where we've got 20 amino acids and 4 different DNA letters, right? A, T, C, G. So what we find is different languages in the cell, multiple overlapping codes. But when it comes to proteins, coding for proteins specifically, 3 different DNA letters code for a single unit of a protein, right? An amino acid. And so what we actually find, and this is what Snake was talking about earlier, is we find redundancy in DNA when coding for a protein. You'll oftentimes see it described as 3rd position codon degeneracy, I believe it is. And so we've got this wobble position 3 that is redundant. And so if you were to change that, it's not going to affect the protein. And so some would say it's absolutely neutral. But what we're actually finding is that wobble position 3, your third position codon variation, it's not simply just redundant. It's not simply just tolerating error, but, and there's secular papers describing the fact that the cell is actually using these different redundant elements to slow and speed processes in the cell. So we have just amazing levels of information compression into every letter of DNA. And so, yeah, those can be hit with a mutation. And although it doesn't affect the protein, I would argue that it's still slightly deleterious because those redundant elements are used to slow and speed the processes in the cell. And so if it's hit with a mutation, that speed changes and it could change negatively. Not to mention redundancy. I'll say this and then go ahead. Redundancy is good design. And so more redundant elements in the genome that are hit with deleterious mutations leaves less redundant elements in the genome to be utilized as backup code, or even much like a spare tire in the back of your car. Yeah, it's redundant. You got 4 tires. Once you use it, I know the evolutionists love the car analogies. Once you use it, well, that's it. There's no other spare tire. Now you better not get another flat. And so redundancy is important. Go ahead, Taylor. What are your thoughts on that?
So, I mean, there are some very niche reasons why there's like weak selection for certain codon bias, like for CG tags, for example. Their viruses get noticed by the cell, so they're actually selected against having that. But overall, the selection is really weak, and the distribution of codon bias is basically random. So the majority of the synonymous mutations are going to be just the same if they're being translated. It's going to result in the same protein.
Okay.
So how much time do we have left?
Yeah, let's do this. Praise, since we've already gone over on the discussion.
Oh yeah, we're way over.
Yeah, let's jump into closings. I'll do my 5-minute because I started. Snake can do his 5-minute. This has been comprehensive. We'll do some audience questions and then we'll wrap up the podcast. It's been a lot of fun. So okay, so Praise, I get the first 5 minutes.
Yep, you started.
Okay, so excellent discussion. You know, I've had a lot of fun here. It's been comprehensive. Praise, let me know when I have a minute left, if you could. And so essentially, it comes down to whether or not these examples of localized improvements that I would say are going to save the day for genomes, because deleterious mutation accumulation, my whole argument is that they put shelf lives on genomes. Okay, and this is actually amazing evidence from the Bible. We have profound biblical evidence for genetic entropy, because the biblical account of the patriarchs and their ages pre and post flood that we read in the Bible actually reveals this classic genetic degeneration within humanity when you start with Adam and Eve. And so this is biblical. And when all the relevant data is plotted, all these populations show a classical decay curve that approaches 0, which is exactly what we see with your low impact deleterious mutations that are accumulating. Now, here's the problem, though. His arguments are basically like trying to remove rust one atom at a time, very occasionally. And Taylor, I mean, it's kind of tongue in cheek, but he keeps on saying that selection removes unselectable mutations. That doesn't even make any sense. That's the whole point, is your low impact mutations, your slightly deleterious mutations are effectively neutral. They're only slightly deleterious to the point where selection can't see them. And so they're only subject to genetic drift. And that's the whole point of why it's just completely arbitrary to ask who is the most mutant. Because the entire population has accumulated mutations from previous generations. The population in general is multiply mutant. And yes, I agree, some may be less mutant than others, but they are mutant nonetheless because they have inherited mutations from their parents and grandparents. And so synergistic epistasis is actually only going to make the problem worse, because you're just going to get localized subgroups essentially that experience rapid extinction, but the whole population is still mutant. And so, no, you can't select unselectable mutations. And yet those are what? Low impact. They're deleterious. And so I appreciated Taylor. He gave some examples of very bad fitness declining mutations, and then secondary mutations, right? Compensatory mutations was a bulk of his argument, that apparently make it slightly better than the terrible fitness that pre-existed. And so again, what I've said in response this whole time is those types of compensating mutations, they're only slowing down the degeneration, and they are not stopping the process. Okay, so these slightly deleterious mutations that are low impact, they are the problem. They accumulate unchecked, they degenerate. Recombination isn't going to save the day, because again, recombination is just going to do what your synergistic epistasis does, your rare beneficial mutations perhaps, is you may have a localized increase in fitness, but while the whole genome is degenerating, and you may have some localized improvements at a few nucleotide sites, massive numbers are still being degraded. And so there's no positive trade-off. It's not sustainable. It results in exactly what we've seen in the E. coli experiments with shrinking functional genome sizes. Essentially, what you're doing is you're just throwing out a ton of information from multiple nucleotide sites, and then you're trying to desperately replace all of that information loss with single desirable point mutations. It's not going to work. It's not going to save the day. And we see thousands of mutation-related diseases manifesting in the human population. There's a paper out there that talks about how just mammal mutation rates in general are all very high. How many billions of dollars has been spent studying the human genome? So yeah, we have more evidence for degeneration in the human genome than, let's say, other species in the wild that we haven't really studied. But the more we study those species in the wild, I predict, yeah, you're going to find evidence for disease, degeneration, because species with high mutation rates, long-lived complex organisms, they are going to be consistently more and more mutant. And that's why we have so many examples of what I call microgenetic entropy, the entire hominid fossil record, basically, or those in the human line. So your hominin fossil record, like Neanderthalensis, highly inbred, suffered from a high genetic load, mammoth populations as well in the past. Your hobbit species was suffered from reductive evolution. Homo naledi, Homo erectus. Again, we have localized examples today, butterfly populations. Because if you want to see a sneak preview into where we are going genetically as a species with genetic entropy, just look to what occurs with inbreeding. And yes, mutations accumulate and mutations add diversity because they're adding something that was not previously there. But the type of diversity that's being added is the type of diversity you get after copying out a book 200 times, and it's more diverse because you have all these typographical errors. Okay, or what about all of, the dents and rust marks and scratches that accumulate on a car over time? Sure, it's more diverse, but it's not diverse in a better way. Your book has descended into gibberish, and your mutations that accumulate in a large population, firstly, there's a lot of noise. Praise, how much time do I have? I think you're muted.
Whoops. I'm sorry, Bad. You're a minute over, so if you wanted to wrap it up.
Okay, I'll wrap it up here. So Praise, you got to learn to click the unmute, but you're doing good. So here's the last thing I'll say is one of our next discussions needs to be on junk DNA, because a lot of the arguments put forth by Taylor in terms of the mathematical models do assume a mutation rate of 1 per generation, maybe 5. But if you're 10 or more in terms of functionality, 10% or more, I'd argue that the genome is about 80% functional. That's 80 deleterious mutations. Then these deleterious mutations, they really do put shelf lives on genomes. And so here's the last thing I'll say. If species cannot persist for millions of years into the future, they definitely could not have persisted for millions of years into the past. And so the reason why species have not yet gone extinct is because biology is young. And I'll yield there. And to be fair, praise, please give Taylor equal time that I took.
Absolutely, Taylor. Go ahead and take 20 if you need it.
Oh, I think you're muted too, Taylor.
Did you mute me? Or did I mute myself? I don't remember.
I muted you both before I started because I can't stand background noise, and you both obviously didn't notice. So go ahead.
Yeah, you hear my rustling notes. All right. Now I just mixed my notes up. Okay. So yeah, where do I start? So I asked multiple times where the actual empirical data was for genetic entropy, not just certain populations that have low selection, that have inbreeding issues. We know these are problems. This is not synonymous with genetic entropy. Genetic entropy is much more strict than that. It has to be universal. There are preclusionary defeaters for this, such as the T7 bacteriophage I brought up, which was saturated with mutations. Average fitness went down, but maximum fitness went up, which means small amount of individuals were actually more fit because of mutations. The majority of the population had bad mutations, and the bulk of the population fitness went down. That's fine, because if there's a numbers game, if the population's high enough, some combinations will end up being better than even the mutations you started off with. And yes, you do get more and more mutant over time. Evolution assumes this, that we never considered that a problem. And that's fine, because compensatory mutations are part of that mutation. More and more mutant every generation. They'll fix whatever's left over from the multiple selection processes that get rid of tons of bad mutations. Yes, humans may be a population where selection is not sufficient. But again, that is not evidence for genetic entropy as the concept that is inevitable, unstoppable degeneration of all genomes. Now, it seems that you mentioned a paper called something like, "Can simple organisms get over genetic entropy?" And this to me seems to be basically conceding the point, where if you're moving on to this argument of, okay, well, only complex organisms suffer from genetic entropy, then that's kind of already conceding the point that some organisms are not affected by genetic entropy. Now, you may want to just change the definition of genetic entropy as only applying to complex organisms. That's fine, but I think that does show that in general, there are examples of preclusionary processes in some organisms that are against genetic entropy, that genetic entropy said was impossible. Okay, so they're adjusting the model. But I'll just go over the other couple examples I gave. The N1 influenza, it had mean fitness wild type. It was fit for its environment, as you'd expect. It's given, a score of 1 for its fitness, wild type. So it had H274Y mutation, big hit to its fitness. It was almost half as fit as before. And then I believe that this was a heterozygous combination with the R194G mutation. Together, the deleterious mutation plus this new mutation actually made the influenza more fit than the wild type. Same thing happened with Salmonella. It had a mutation which conferred it the advantage of antibiotic resistance. It was a trade-off. It was less fit in general because of this. It was less reproductive fitness. Then it went through another round of several mutations, and it recovered that genetic fitness, reproductive fitness, and kept its resistance gene. So it had that original mutation for the resistance, and then it kept getting more and more mutant, and it actually got more fit. It got more traits. It got more functional, and unlike Lenski, it was actually put back in wild type environment, and it was more fit, and it kept the benefits that originally it traded off. So what we observe in evolution is peaks and valleys of fitness. But the fact that there is actually an increase in complexity, an increase in fitness, would actually preclude the definition Sanford gave for genetic entropy. And so now the model is adjusting to maybe only apply to complex organisms, which of course are harder to study. And so, yeah, I think that that's the point that we're at, is where we've shown that there is no actual empirical data backing up genetic entropy. It's only computer models. There's a mutational paradox where very simple math seems to indicate deleterious mutation accumulation is going to be a problem. There are multiple models that show that that can actually be overcome by multiple processes. We don't know exactly which one it is. If any of them are true, it could be any of them, it could be all of them. But it's a paradox because in reality, in populations, we don't see that. And for more complicated populations, we can look at mice. The Amazon Molly I brought up. These are fast generation, and the Molly is non-recombining, so it's at more of a risk. It still obeys the paradox where it's not going extinct. So there's nothing that really precludes the idea of genetics being a self-regulating thing where it can handle, there's a mutation selection balance, and there is preclusionary evidence for genetic entropy. And so I think that'll do it.
All right. Thank you guys for those closing statements. It looks like the audience really enjoyed the discussion. A lot of good reviews so far. So that was a lot of fun. And so we'll head into a few questions. You have a few of them, so I think we could probably get through these if we hustle. So maybe keep between a 1 or 2 minute answer, within that time frame, and we'll just try to close out here.
Yeah, take your time. I don't mind. I don't mind questions.
Excellent. So our first question is from Echoing Erudite. Question for you, Donny. Do we know how much longer humans last with genetic entropy before we start to go extinct?
Good question. I think it's too difficult to put an exact number on because there's just so much going on in the genome. See, if we were not designed with what I described in the opening statement, these intricately designed DNA repair enzymes, we would have gone extinct after a few generations. We have a lot of DNA breaks, millions of DNA breaks. And yet these DNA repair enzymes fix the majority of them. Now many do get through. 3 new mutations, I believe it is, per cell division. And so we would have gone extinct a long time ago if it weren't for these DNA repair enzymes. But every generation gets more and more mutant. I think there's just a lot of factors to consider. We know mutation accumulation puts shelf lives on genomes. We see what happens with smaller populations. Just look at Neanderthals, for example, Homo floresiensis, mammoths, high genetic load. With a large population like humans, 7 to 8 billion people, there's a lot of noise in the genome. And so one could say, 300 to 400 generations. Most Christians would probably say Jesus will return by then. So a good question, though. I don't think an exact number can be put on it. Appreciate it.
Thank you so much, Donny, for that detailed answer. If you want to respond to that, go ahead, Snake.
Oh,
mute.
Snake, I think you're on mute. Oh, he might have. Taylor, you there? You might have stepped away for a bathroom break.
Yep, muted. No, go ahead and just go to the next one.
All right, Tanya Brown, for you, a question for you, Snake. If most mutations are deleterious, wouldn't the first simple cells have died before mutating enough compensatory mutations, especially before developing repair genes?
Well, like I said, it's a numbers game. So as long as you're able to keep replicating, some of the children are going to have the good mutations. Some of them are going to, and a majority of them are going to have the bad ones. But it only matters if you can keep going through the small number of well-mutated children.
Praise, can you re-say the question? I'll see if I want to say anything to it.
If most mutations are deleterious, wouldn't the first simple cells have died before mutating enough compensatory mutations, especially before developing repair genes?
Right. I would even ask the question today, would compensatory mutations reverse the effects of even, 1% or 10% of all deleterious mutations today? Because there is a lot of deleterious mutations that accumulate. And I would say you're going to need a lot of these more or less rare compensatory mutations to counterbalance the damage. You want to go all the way back in time to your single-celled like ancestor that evolved into a multi-celled ancestor, into a fish, amphibian. I mean, once you get into your, farm, right? Fish, amphibian, reptile, mammal. Once you get into your amphibians to reptiles to mammals and higher, more complex organisms, that's where I would say the biggest issue is. Genetic entropy is a concept that was written for higher organisms, longer lived organisms with shorter generation times, faster mutation rates. But here's the last thing I'll say, and then Taylor gets the last word. Question was for him. Lenski's bacterial population experiments. His bacterial populations have shrunken functional genome size. They've experienced reductive evolution, and they are degenerated. They are handicapped. So I would argue that even in bacteria, that we could say, well, maybe bacteria is one of the only organisms that can withstand. And again, I just wrote a 17-page article on it. I recommend people check it out for this debate specifically. And even bacteria are susceptible, it seems, to genomic decay. I yield.
Go ahead, Sing.
All right. So, yeah, Lenski bacteria are not handicapped. They aren't losing any genes they need to survive. Their fitness is not actually going down. They are not selecting for any of the mutations that happen to the genes that they don't need because it doesn't matter. So back to the original question, those first cells, taking your argument, they're simpler. So mutation, deleterious mutations are less of a problem for the simpler organisms. If we're going to take that argument that it's more of a problem for more complex organisms.
Thank you so much. We'll into the next question. So this is for you, SFT, by Mark Reed. Why do you refer to Kayuma, I'm not sure, or Kimura, I'm sorry, okay, when Kimura himself disagrees with Stanford and has said that he is using his work incorrectly?
Kimura has, from my understanding, has never said that Dr. Sanford's using his work incorrectly. Let me see. When did Kimura pass away? So yeah, I'd like to see a citation of that. But Kimura, in his work, Dr. Kimura, he put forth a model that shows how many low impact these nearly neutral mutations are accumulating. You got this massive no selection zone. But he did say in passing, more so an assertion or a claim that adaptive substitutions or adaptive mutations, basically beneficial mutations, should be able to counterbalance the damage. But that's it. He never gave any data to support it. What do we know today? Well, there's been a lot of research since Kimura. We know beneficial mutations occur, but they occur very infrequently. It's about 1 in a million. Okay. And when they do occur, they're still usually reductive and functionally compromising to the respective organism. And even when they do occur, they're often lost due to genetic noise, because selection doesn't see them, especially in a large population, and therefore selection doesn't amplify them. This goes back to my opening statement where I talked about what's called selection interference, where you have so many traits segregating in a large population that they're basically working against each other. And so selection is only able to amplify the best and remove the worst. And so the last thing I want to say is beneficial mutations almost never get fixed in populations. And if they do get fixed, Dr. Kevin Anderson, in a debate on this channel with Jackson Wheat, he showed a paper, I believe it was from 2020. And, I've got my slideshows, of course, but this is a podcast debate. And so this paper talks about how the beneficial mutations observed in Lenski's bacterial populations, they're actually starting to die. So, I mean, there's just so many problems with beneficial mutations that Kimura's statement or claim, it doesn't work. It's been falsified, basically. But he never gave any supporting evidence for that claim. And so it wasn't a misrepresentation, therefore. Anyways, good question. I appreciate it.
Go ahead, Snake, if you can respond to that.
Yeah, so Kimura says that directly to Sanford, this is a quote from Kimura: "The situation becomes quite different if slightly advantageous mutations occur at a constant rate, independent of environmental conditions. In this case, the evolutionary rate can become enormously higher in a species with very large population size than a small population size, contrary to observed pattern." And basically, I just found this, but I think this was his response to Sanford, but it echoes something that he said in the paper, which was very similar, which is basically that if you, since his model oversimplifies things, which we have to do in genetics because it's very complicated, and he's just looking at neutral selection, that oversimplification doesn't mesh well with adding in the beneficial mutations. And so if you add in the beneficials, there's runaway evolution, like in the positive direction. So the and that's assuming constant rate too, which is also not realistic. So the beneficials were actually too good for realistic models, which is why he takes them out. But then Sanford bases his entire theory on this model that's not supposed to be used that way.
So I guess as a last word, I looked it up. Motu Kimura, 1924 to 1994. So I'm highly skeptical that Kimura has ever said anything directly about Dr. Sanford's claims. Dr. Sanford, if I'm correct, did say that he would suspect that Kimura would have drawn on the curve, nearly neutral mutation curve, or no unselectable mutations, a very similar curve with beneficial mutations, because if they are rare, And even when they do happen, they're mostly reductive, context dependent, I understand. But when you actually look, see, a lot of times we got to look under the hood of the car to see what's really going on, right? And so when you look to the genotype rather than the phenotype with a lot of these mutations, that's where you realize, wow, this advantage, this adaptive episode was actually due to a loss or the breakdown of a pre-existing system, or, you know, a promoter that's now unregulated, almost like keeping your light switch on all the time and, you know, you can't turn it off kind of thing. Or, you know, your alarm clock breaks where it's just always on now. I mean, it's not really a benefit. It's a breakdown of some kind. And so that's not going to counterbalance the damage. But Kimura did say adaptive mutations should essentially counterbalance this issue. But I think that this claim without evidence has really been refuted. It's really been falsified, basically based on what we now know about beneficial mutations and what occurs on the genotype with a lot of, I'm not saying all of them, but with a lot of them. So I'll yield there.
Thank you so much, SOT. We have a super chat. Let's see here. It was up there. I have to find it, but he says, welcome, or he says, hey, everyone. He put his hand up. It was, oh my gosh. It's gone now. Like, what happened to
Gmos?
Somehow. Yes, Gmos.
Yeah, he said, hi, everybody. So hello, Gmos. Appreciate the support, brother.
Yeah, Gmos. There it is. I found it. Okay. Very good. Let's go on to the next question from Centurion 737. For you, Snake, if mutations are reductive and harmful and diseases are mutation, why do we still have disease when you claim they are being removed from the human genome?
I explained a few times that it doesn't remove all diseases. It will only remove just enough, basically, to keep you at that mutation selection balance. So it's not purifying your whole genome to make you a perfect being. It removes enough so that you're not dying or not failing to produce children, but things like bad knees, bad eyes, you know, whatever else, you got dry skin, little things like that you can survive with, it is not going to get taken out.
Go ahead, SFT, if you want to respond to that.
You can move on to the next.
So we have another one from Mark Reed coming at you. SFT,
I wouldn't expect any less from my boy Mark.
He says, you claim Mendel's account has been published in journals. Has it been published in peer-reviewed genetics journals? And has genetic entropy been accepted by scientific consensus?
Appreciate the question, Mark. Also looking forward to Mark's upcoming debate with Paul Price. That's going to be a lot of fun. So one that comes to mind, and I've got a ton in my slides here listed. There's quite a few. Now, what you have to do is sort through ones that are published in secular journals and others that are through a symposium or even in creationist journals. But there's a solid mix. One that comes to mind, I think, that directly answers this question was Dr. Sanford and Dr. Carter published in Theoretical Biology and Medical Modeling. So I believe he was looking for a paper published in the peer-reviewed journals that have to do with either biology or genetics. So the name of this one, Snake has a problem with this one, but I mean, in the discussion, I'd like to see an actual sophisticated critique, not just from some YouTube video or some angry blogger, which, by the way, the arguments put forth earlier from Taylor are very similar to arguments put forth by Dr. Dan Stern Cardinal, Dr. Rob Carter, who was co-author of this paper, peer-reviewed in the secular journals, he responded on CMI to these arguments. So the authors would disagree with those critiques, but it's called A New Look at an Old Virus, Patterns of Mutation Accumulation in the Human H1N1 Influenza Virus since 1918. And so basically in this paper, what they discovered was the H1N1 human version. And Taylor disagrees with it, and he'll have a chance to respond. But in a nutshell, the paper itself demonstrated that this virus went from a red-hot pandemic to a whimper to an extinction event in 90 years. Now, we do have the swine flu versions now circulating, but that's different, okay? And this was due to a linear accumulation of mutations. This is Genetic Entropy at Work, published in a secular journal. And the problem with the evolutionists, they can't really explain why the H1N1 virus is extinct in humans. Okay, and so basically, and I'll wrap it up with this. You could read the paper, it's technical, but in a nutshell, the virus started off more human in its codon usage, but it randomized over time. So it ended up more randomized. And how we know this is because it became worse at interacting with human DNA over time. And so if it is using the wrong codons, that means it will be less efficient at replicating in human hosts. And so this is just a clear example of a decline in functionality. And it matches exactly with genetic entropy. And so I'll yield there.
All right. So yeah, they failed to actually measure direct fitness, which was reproductive capacity. And Dr. Dan actually asked Dr. Carter, and his reply was they didn't compute any growth methods, and their work was done only on the computer. So with codon bias that you were just talking about, that's pretty normal for viral distribution. So, and I think Dan actually published a paper on that. So that's not a very good measure of their fitness. And the other measure of fitness was virulence, which virulence always tends to go down in a pandemic because it's not a good strategy to be very virulent when everyone's already infected. It's actually a better strategy to become less virulent. So as the pandemic goes on, a less virulent virus is actually going to be becoming more fit. So another flaw in the study was that they actually were comparing an avian origin flu with a human origin flu and conflating them. So they can't actually show. There was no direct measure of reproductive fitness, and they can't show any causation between that and well, they can't show a hit to fitness, but they can't show any causation between what they actually measured and the extinction.
Okay, so last words, and I've got it pulled up here. It's a long response from Dr. Rob Carter and Dr. Sanford on this paper. Again, published in the peer-reviewed literature. It's my understanding Dr. Dan Stern-Cardinal did not respond in any meaningful way in terms of the secular literature or anything like that. And so it's titled, I'm looking at it right now, and it's quite detailed. For sake of time, I'm not going to read through it. But it's called Responding to Supposed Refutation of Genetic Entropy from the Experts. Highly recommend that people check it out. But based on what I know, okay, is that codon bias declined consistently over time. And that's not consistent with adaptive evolution. I mean, it shows clearly that they got worse, not better, at interacting with human DNA. And that would correlate to slower replication. And that means less lethal infections. Here, it's basic. The viruses became less lethal because they got worse, not better, at doing their one and only job, which is replicating themselves. And so again, this went from a red hot pandemic to a whimper to an extinction event in 90 years. And adaptive evolution does not cause extinctions. But if you want to see a direct response to arguments from Dr. Dan Stern Cardinal, but Dr. Carter and Dr. Sanford responding to him directly on this paper, check out Responding to Supposed Refutations of Genetic Entropy from the Experts. I yield.
If I could get in real quick there. So that wasn't actually the results that they got. They kind of extrapolate some other things within non-peer reviewed literature that is not actually published in the paper. So all they actually report in the paper is they document multiple extinction events, and they report the change in codon bias, and they observe a continuous erosion of that's the codon bias, and they observe accumulation of mutations. They don't actually report in this paper that it was caused, that the extinction was caused by these things, and so it could have been due to human vaccination. And you said they got less lethal. Well, lethality is not a measure of replicative fitness. So,
well, when it comes to the virus, if pathology or pathogenicity, if that is the correct way to define fitness with these viruses, and if
it's not, sorry.
Okay. So what's the appropriate way to define fitness in the H1N1 human virus? I mean, if it's getting worse at interacting with human DNA over time, how is this not an example of, and I'm looking at his article here, and he's, from the data he presented in response to Dr. Dan Stern Cardinal, Rob Carter says, we were able to discern that the virus had been picking up about 14 mutations per year of circulation, accounting to over 1,400 nucleotide changes, nearly 11% of the genome. We were also able to show that the genome was moving toward a state of maximum randomness. That's what I said, that it's been randomized over time. You're saying that's consistent, apparently, but it wasn't becoming better. Instead, the laws of thermodynamics were driving it toward a state of maximum entropy. And so this seems to be, this trend towards randomness was documented in the original paper. And Dr. Carter points out that it was reinforced with additional publications later. And he's got 2 citations here. So I don't know. Go ahead. You want a final word on that one?
Sure. So reproductive fitness is the measure of fitness. It's not always a good idea to give your host symptoms, and especially not a good idea to kill the host, because then your host dies, especially late in a pandemic. So sometimes you do want them to have symptoms because that's one way it spreads. But it's very well known that diseases do not survive well if they kill their host too fast. So lethality is not a good measure of that. And vaccination explains the extinction.
Yeah, but without a host, how can they reproduce? They need a host to interact with. But it became worse over time at interacting with the host. That's not helpful. And then it was,
but that's not
into
that's not reported in the paper, though.
Well, they say that
I think we should probably cut it off here, because it'd be a whole nother debate in its own question.
Yeah, we'll do this paper.
Well, you know what? That needs to be a debate between Snake and the author of the paper. That would be fun to watch. But anyways, yeah, no, I appreciate that interaction. But
yeah, I think we're going to have to start winding this down, because Grayson's been waiting for an after show for like an hour and a half now. So maybe we should probably cut her short here. But yes, Grayson, I would like to be come over there and discuss genetic entropy with you. And yeah, everyone check it out. So if you want to shut her down here, SFT, that'd be awesome.
Never. We're going for another 3 hours, Snake.
Where's the after show at?
On Grayson's channel. It's base theory. Familiar. That's his.
I'm still. I see molasses in the chat. Come on, I'm waiting for you to man up and come join me in this podcast or a debate. So, anyways, if people enjoyed this was episode 1 of this podcast. I enjoyed it, and I've got a few more planned. And so for people that want to do, more of podcast related debate or discussion, in this specific one, we had formal statements and rebuttals, very good discussion. And so if people enjoyed this, if they appreciated it, if they're looking forward to seeing more of these, please leave your comments. Let me know. Give me your reviews. As people know here, we're doing this full time. We got a ton of debates, 4 to 5 a week. And so I thought it'd be nice to mix in these podcast style discussions as well. Helps me to squeeze in a lot of the discussions that I want to have personally, since I'm left moderating a lot of debate. So leave your feedback, leave your comments. I love the topic of genetic entropy. I'm fascinated by it. Taylor, I mean, you and I basically have been discussing this back and forth for 4 years. So this is fun, my arch nemesis, one could say. So thank you, Snake, for doing this. It was a great first episode. Hope you enjoyed it. Why don't we give you some final words, final thoughts as well?
Yeah, thanks for having me for the first episode. And I guess I'll just say, I think I found out that quote was Kimura, but it was someone else quoting him to Sanford. So I think that'll correct the record.
Okay. Yeah, that makes it, because I mean, Kimura was born in like 1924.
Yeah.
So I don't think he was responding right to Dr. Sanford. Praise. I did notice a super chat came in.
Yes, I know.
So why don't you sneak it in for Taylor, and then we'll completely shut it down.
All right, Taylor. Humans lost ability to climb trees, run faster, lost fangs, lost fur, and takes a full year to walk, 10 to 15 years to even fend for itself. How is he the fittest to survive?
Because we get to sit on the couch playing video games instead of hunting in the forest. And we get to sit on YouTube and argue about it. I think we traded off pretty well. Pretty good trade-off there.
Thank you so much for that response. I mean, SFT, if you really wanted to, go ahead and make it short.
No, we're going on 3 hours. So that was fun. Praise I am. Great job moderating episode 1. Privileged to have you. We'll definitely have you for more. You know what we'll do? We'll have different guest mods every podcast. So anyways, to the audience, hope you enjoyed it. We were originally just going to pre-record these and then upload them later. So if you appreciated the fact that we did them live, and then I'll edit it a little bit, just like the opening intro music and stuff. We'll get it up on the podcast website as well. So with that, everybody, thanks for tuning in. Hope you enjoyed the podcast debate, the SFT podcast, Creation versus Evolution Conversations. God bless.